Hello, everyone. Welcome back to the mathematical analysis after the Independence Day holiday. Last week is I just entirely on the vacation to celebrate July 4th in Seattle. I have not renewed any classes. But today, well, beginning for the last half of this summer courses. I remember last time we have talked about cardinality and like how to compare different size, how to compare the size of different set, including the Cantor theory and pigeonhole theory. Let's move something different today. So today I think it is a topic about abstract algebra. It's a beginning. It's something called number theory, but it's not a very hard number theory. It's just an introduction to number theory. We'll mostly focus on the prime numbers, introduce the prime numbers, what's the definition, and how different numbers can divide each other. And that's the main goal for today. Yeah. Maybe include some like one or two examples about congruence classes, and that's it. So it will not be very hard, and it's just like a setup for the afterwards material. Because in the next class we'll introduce about the axiom of real numbers. So today we'll get some feeling about some mathematical thinking. Okay, so the first topic we want to talk about today is operations. Operations is very simple. It's just like addition, multiplication, minus, divide, power. All of these are operation, but maybe previously you don't recognize operation as a as a function, but today we'll define it as function. So it's defined on a set, non-empty set S. It has some element, or we have nothing to do the operation, and a binary operation, which is the basic form on S, is a function, usually denoted by some star-shaped things, and it's going from the S Cartesian with S to S. So which means like for example, we do the addition. So we do 1 plus 1 equals to 2. So it goes from 1 to 2. So this is a function going from the two-dimensional to one-dimensional. So it's a binary. And if it's a dimension more than 2. So we go like from 1 plus 1 plus 1 to 3. So it becomes like S times S times S goes to S. So that's the operation. And a set with one or more operations defined is called an algebraic system. So we no longer treat with numbers specifically, but we treat with some algebraic structure. So that's the operation definition in a formal way to define it. So the notation is for the operation is like that. So for the S Cartesian with S is usually AB. And usually like imagining we do the number addition, then S is the set of R, which is a real number, is the most common. But it can be any set. It can be a set of letters, can also work well. We just need to define the operation by our brain and by our common knowledge. So let's suppose AB from that. Then like this way, you can see here, this is a very common way to define a function. It's like a function of some element goes from to something, maybe C. But here we usually do this. And this is traditional way when we write A plus B or A minus B. So we usually write the notation of the operation in the middle of two elements from the set. So this is just a notation of how operation works. And this is read as the operation star applied to AB. So let's see one example. So suppose S is the real number set R, and obviously 110 is from S, then operation plus, very common. So 110, this one is what we want to do, the operation 110, two elements, we want to plus them. So it's like 1 plus 10. We write the operation sign in the middle, and we can also write this one. This is a function form, and we get 11. So this is how we do the operation, very basic. So there's usually some properties of operations. It doesn't mean like every operation have these properties, but it's just like some common properties of many operations. So one operation is called commutative. it's like A, for example, A plus B equal to B plus A. So addition is commutative. Association is like to do the formal thing first, is equal to do the later part first. And this is associative. And we see this very often when we see from set operations. Yeah, set operation is an operation. And we can see like the union set, or even in the logical operations, and all, they're all operation characters. And remember, they're all commutative and associative. Yeah, maybe it is. So, and another property we may not seen before, but perhaps seen before, is identity element. So identity element, you can see it doesn't apply any new functions to the algebraic system. For example, if E is usually we denote as identity element, and E operation with A is equal to A operation with E, which is equal to A. So we can do both form too. So one famous example is 1. 1 is if we do the multiplication of any real number, is equal to A times 1 is equal to A. So 1 is the multiplicative identity, and 0 plus A equal to A plus 0 equal to A, which is a additive identity. Or we can say it's a identity element for addition, right? So one example is for a non-empty set S, we define operation question mark. We do the question. So what is question? A question B is always equal to A. So let's see how what property it has. So actually, the question is takes order pair AB to its first coordinate. So it's just simplify AB to A, right? So is it associative? Yes, because it's always taken first. So if we, for example, if we do B question with C, we get B, and A with it is A. And we do the formal part, we do AB is A and AC is A. So it's same, but it's not commutative, because A question B is A, but B question A is B. So it's not commutative. Does it have an identity? Well, I don't think so, because just because it is not commutative. So like, for example, you have one element, like A for all elements A, like maybe it's not star anymore, it's become question mark. A question mark with E is not equal to E question mark with A, which is violate this first part. So it doesn't have an identity here. Okay, so the first theorem I'll see there is only one identity. So how do you prove like at most one, or yeah, how do you prove like at most something? We just need to show there's no two element. So if we want to prove exactly one, then we first show its existence, then show its uniqueness, but it's at most. So we just need to show its uniqueness. Okay. So suppose there's two identity element E and E1. Okay, for operation, this is a operation can be anything. So first, like E operate with E1 is equal to E1. This is by the identity. This is by identity property, right? So imagine E is identity. So times not times, but operate with E1 is equal to E1. And remember, E1 is also identity, so it operates with E is equal to E. So in this case, we have something very interesting. Is E equal to this one, equal to this one, because we can do E1 operate with Z back by this property. So we get E1. So they are equal. So there only exists one identity. But this sign might be not correct, because it's at most, it doesn't ensure it has one, because the example before we just said, it doesn't, some operation like the question mark there doesn't have identity element. So if any operation have a identity element, it will also have a inverse element. So how to say it has a inverse element? We'll see here. So for any operation star on the set S, if it has an identity, E, then for all element A, if there exists a B such that A star B equal to B star A equal to E, then B is an inverse of A respect to star. So it doesn't always ensure it has a inverse element. But if it has, it operates with another element. We can always find another element to operate with it to be the result will be the identity. So a notation here, remember we previously do such that is written by SD, and WRT is usually write as respect to. So respect to from now on we'll write WRT. Okay. So let star be an associated operation on set S with identity E. Then A has an if A has an inverse element, then it has only one. So what does that mean? That means we'll prove its uniqueness, but not existence. So it may not exist one, but it only has one. So here we'll do the proof of it. So first, suppose A has two inverse, right? And we'll show B1 and B2, they're the same. So first we do B1 is equal to B1 times star with E. This is true because identity element is always exist when we considering the inverse. Inverse element is based on one operation has one identity. So this one is also true. It's always true. And because like A has identity B1 and B2, then E can be written as A with B2. And by associativity, we can do this operation first, and this becomes E2 because B1 is an inverse of A. So it proves B1 equal to B2. So there's only one inverse P1 for A if it exists with respect to the operation star. Okay, that's all we want to talk about operation. So just like define how operation is and with some basic properties like identity, inverse commutativity, and associativity. So that's all. So let's go to divisibility. Divisibility is not in the field of operation, but it's always very common when we study the studied division in elementary school. Remember, some numbers we say they are divisible and some others are not divisible. So here we'll see that in a higher level definition. So divisibility is always considered in integer when we study division first. We are not going to usually it's not very common to say, well, something is divisible regarding all the real numbers. That might be something very crazy because real number is always divisible in the real number set, right? So suppose AB is in the set of integer, A is not zero, then if B is equal to AC, A times C, there is this one C equal also in the set of integers, then we say A divides B because A can time integer equal to B. Or there's some like common way to say, there's many ways to say it. So first we say A divides B, or A is a factor of B, A is a divisor of B, B is a multiple of A, B is divisible by A. And this is all very common knowledge we heard about. And if your first language is not English, it is very easy to get like confused about or which divides which, because if we say A divides B, which means A is usually we say is a smaller one, B is a larger one, but B is divisible by A. A is a smaller one, B is a larger one, but they are in the opposite direction. So, but if you familiar with these 5 language here, it will be very easy to understand. And this is what we write mathematically. We'll write A divides B. So A divides B, which is like very easy to see. And the negation is A doesn't divide B. And we'll add one slash here to denote it's not divisible by it cannot divide B, and B is not divisible by A. Okay, and there's also another definition called proper divisor. So A divides B, it can be equal, but a proper divisor is A divides B, and at the same time, the absolute value of A is smaller than the absolute value of B. and we say like A is a proper divisor of B. And this is very similar to a proper subset, like for example, if A, B, they are sets and A is a subset of B, and at the same time A is not equal to B, then A is a proper subset. So proper divisor is a subset of divisor set. Okay, and some example of that is 3 divides -15 because we can compute as -5. 6 divides 18. 17 divides 0. Very yeah, this is very interesting thing. Like every number divides 0 because because you can imagine it like 0 divides anything is left with 0. So 0, everything is divisible by 0. -5 divides 20, yeah. 6 divides 1, no, because 6 you cannot find an integer like times 6 that equal to 1. But you can always find an integer times a 7, like you can always find an integer times 17 equal to 0 because 0 times 17 equal to 0. So that's how we saw it. And 6 not equal to 3 because 6 times 1/2 is equal to 3 and 1/2 is not an integer. Okay, and there are two related theorems regarding the divisibility. The first one is if A divides B, B is not equal to 0, then A must be smaller or equal to B. And the second one, so probably we'll first see the proof of the first one. So because A divides B, then by definition, B is equal to AC and C is an integer. And because in the assumption here, B is not equal to 0, so AC is not equal to 0. AC is equal to B, AC is not 0, which means A not equal to 0 and C not equal to 0 because if A is 0, then AC is 0, C is 0, and AC is 0. So they must not be 0 at the same time, right? And because C is not equal to 0 and C is an integer, so it must be like, remember, integer doesn't contain 0.6, 0.5, something like that. So C must be smaller or equal to -1 or larger or equal to 1 by integers definition. So the absolute value of C is greater or equal to 1. So here, one very interesting happen is like the absolute value of B is equal to A times C's absolute value, which is greater than here. This fact we might not seen it before, like the absolute value of A times C is equal to the time together. This is, I would say this is not something we call triangular inequality, if you know before, because it's times, it's not like plus. But we can also solve something like that. If it's timing, if the times like -2 times 4 is equal to -2 times 4, then do the absolute value. Because this is because the absolute value is only regarding with the negative sign, the sign negative or plus, and it's always change after absolute values or become positive, so they're equal. And C is greater or equal to 1 here, and this is greater or equal to that, and it's greater or equal to A. So we have proved it successfully. All right. And prove out the second thing here. Well, the second theorem says like if A divides B, A divides C, then A divides B plus C and A divides B minus C. This is very this fact doesn't have many like importance, so we say it's not a theorem, maybe a proposition. Okay, and it's very intuitive. You just write B as A times K, C written as A times N, and we plus them together. K plus M is also an integer. K minus M is also an integer. This is by the fact that integer is a set which is closed under plus and minus. And this fact we'll see in the next lecture when we discuss the integers set property. But we can also accept it as a fact. And integer plus or minus integer is always an integer. So we proved K plus M, K minus M is in the set of Z. And we have proved it. So maybe this lecture is in a like in the reverse form, I realized like many of the fact used is actually in the next lecture when we use the fact of the 13 axiom of real numbers. So probably it's too advanced for now. Yeah. And the next topic is prime number and composite number. So prime number is defined as a natural number greater than 1. So prime number is starting is 2, which is not a product of two smaller natural numbers. So this is defined well because imagining greater than 1, so means it starts with 2 and it's not a product of two smaller natural numbers. It can only have two. So every prime number just have two divisors, itself and 1, because it cannot have smaller natural numbers as its divisor. So if we say P is a prime number, then P is equal to NM, and P greater than N, and let's say if P is a prime number, then P is greater than N, P is greater than N, maybe not correct. P is a prime number, it's a product of two smaller elements. It's not a product, so maybe we cannot write it in this form. Yeah. P is greater than N, and P is, how to say, we might add a negation here. It's not in the case that P is greater than N, P is greater than N. So this is something I write incorrectly before, and this should be the correct form. Okay. And the composite number is any natural number greater than 1 that is not a prime. Yeah, and 1 is neither a prime nor a composite number. So 1 is a very special number in this classification. And if we considering the negative numbers, then the prime number have 4 divisors, including the negation of 1 and itself. So it has 4 when we're considering a large set, the integer set. Okay, and there's one theorem. It's called there are infinitely many prime numbers, and this fact is proved recently. It's a newly formed theorem in the late 20th century, and this is the proving is not very long, but it's very hard to think of it at first. I think the most difficult thing to think about is we defining the M here. Like, so first we'll do mathematical induction. So we'll do a list P1, P2, and to Pn, and to some infinity terms. If we can find such a list, then we say there are infinitely many prime numbers. So we do the mathematical induction. We'll do first find P1 is 2. At least we can find 1, right? 2 is a prime number without doubt. So we can find 1. So the base case is done. And for the inductive case, we'll try to prove like for every set of prime numbers from P1 to Pk, then there exists another prime number Pk plus 1. So here we define another prime number as n. So if we can always find the number n, then we can always find another prime number. And here we do a contradiction proof. So first, suppose n is not prime, then n can be written as p times q, and p and q are two prime numbers. So in this case, if there are two prime numbers, p and q neither of them will be 1. So in this case, it will both be smaller than 1. So n is not a prime. Then because q is greater than 1, because q is a prime number, then p is in here, or if p is not in the case before, it's not here, then p is not a prime, or p is a new prime we want to find, because this is our existing prime list. if P is not in this list, we already find new P. Okay, P is equal to K plus 1, and we are done. So we must assume P is in this form. And Q like Q is something maybe in this form, maybe not in this form, but it's fine. So relabeling the element inside that, relabeling means we can change the order of the element inside, which is very doable. And we can assume like P is equal to P1. And in this case, by the case we define M as the plus 1, we can find 1 is equal to M minus this term, which is here, right? And then we can find so what's special about this term is like because P is equal to P1, then M is equal to P1 times Q, and it becomes this form. So P is divisible by 1 because, well, found here, this is an integer, and P1 there exists one integer times it equal to 1. So P is divisible 1. But remember, like 1 is not 0. So if P1 divides 1, then P must be smaller or equal to 1 by absolute value. But before we find like P1 is a prime, so it must be greater than 1, which is a contradiction. So in this case, M is not a prime. M is another prime which is not in the list. So we have proved it. Okay, and another concept is which is called a twin primes. So a twin prime is a prime number that is either 2 less or 2 more than another prime number. It's in the form of n plus 2, and both n and n plus 2 are prime numbers. And this and combine them all together, we say they are twin numbers, twin prime numbers. For example, 11, 13, this is a twin prime because both of them are prime and their difference is 2. And the famous one is 3, 5, which is the smallest twin prime by absolute value, 3, 5. Yeah, because 2, 3, they're only equal by 1. Yeah, so it's not a twin prime. And yeah, this is another twin prime, somehow larger, 107, 109, they're all prime numbers. So this side is a twin prime. Okay. And there's remaining one question is that if you can prove there are infinitely many twin primes, so it's a question left for you to think about. We have used the strategy to prove there are infinitely many prime numbers, but how to prove there are infinitely many twin primes is a very challenging problem. So I really encourage you to try it. I have tried it, but I have not. I don't find any result, or I cannot prove it. So if you prove it, you are very talented mathematician, I think. Okay, so the division algorithm is something very basic. It's always the first fundamental fact in the discussion of abstract algebra in the algebraic system. So division algorithm is what we learned in elementary school as a division. So if A, B are integers and B greater than 0, then there only exists one pair of Q and R, and A equal to BQ plus R. And R must be smaller or equal to B, smaller than B, then and at the same time is larger or greater than 0. And Q is called quotient, and integer R is called the remainder. Q and R are both integer. And this is like what we do a division, and we can find a quotient and remainder at the same time. But this theorem says like the algorithm, it can only find one unique Q and R. So the proving strategy is to first show its existence, then show its uniqueness. So we first see the proof of its existence. So there are two cases for this. There are two cases for R at first. R can be 0 or R can be non-zero. So in the first case, we say B is a divisor of A, like B can divide A. So we can find the Q in Z such that like A is equal to BQ plus 0. And this is by the fact of 0 is a additive identity element, and A equal to BQ is by the definition of like divisibility. Then we can just define R as 0 here. So we satisfy A is equal to BQ plus R, and Q and R are founded, right? Okay, but there's also another case like B is not a divisor of A, then A is not equal to BQ. So now we can say A is equal to BQ plus R. We add something not equal. And R in this case, R cannot be 0. So R is in this form, right? So we can write, so this is what we want. But we can only have R smaller than B greater than 0. R greater than 0 is easy to understand because it cannot be 0 and it must be greater than 0. We're considering all positive integers here. And at the same time, R must be smaller than B, because if it's not smaller than B, then we can also write A plus B times Q plus 1 plus R. And Q is not unique here. So what we say here is like we can do a graph to illustrate it. So BQ here and A is larger than it, so we can say his R, right? And R cannot go beyond this point. R can at most go to here, slightly smaller. It's not equal. It's smaller than it, because if it's go beyond, then we can say A is equal to some like this is our new R instead of this R. So we have proved its existence of R and Q here. Then the second part is we'll try to find out like, how do you say, we'll find the such pair of Q and R, they're unique. So first, we'll suppose there's another order pair, Q1, R1, such that Q1 not equal to 2, Q, R1 not equal to R. And they are and they're both equal to A in this two form, in this form and this form. And clearly, like if they're equal to A, both, then they're equal. So we can minus Q1 to here and minus R to here, which form this equation. And in this case, because like Q minus Q1, both of them are integers, so this is an integer. So B is so B can divide R1 minus R. And just remember here, like 0 is smaller than R, smaller than B, 0 is smaller than R1, smaller than B, right? So maybe not, because we're considering both cases, it can equal, but this doesn't affect the results many more, because it's smaller than B. And if R minus R1 is smaller than B, something interesting happen, which is say it can only be 0, because if it's not 0, then it must be greater than B, greater or equal than B by our previous theorem. So which means R minus R1 must be 0. So R equal to R1, we prove half of it. And the second part is based on this equation again. So R is equal to R1, so this is 0. And B, remember we say B is not 0. B is not 0, so Q minus Q1 is 0, and Q is equal to Q1. So such QR, the pair is unique. And B is not 0, I think it's defined here, like B greater than 0, so it's not 0. Okay, so from now on, by the fact of 3 existence, for uniqueness, we find there only exists one QR satisfying these two conditions. Okay, so moving to the next topic is called the common divisor. Common divisor also brings about the greatest common divisor. So common divisor is a divisor like for A not equal to 0, B not equal to 0. I remember it's not and but or, which means they're not both 0 for such two integers. And another integer D, maybe A or B, but we also say another integer then to prove it's equivalence, right? So we say D is a common divisor of A and B. if D divides A and D divides B. So every common divisor of so in this case we can say it can divide both elements, so it's a common divisor. And the greatest common divisor is defined in this way. We say if every common divisor of A and B is a divisor of D, and D is a positive number, D is positive, then given D is a common divisor of it, D is the greatest common divisor. So there's there's three assumptions to make some integer greatest common divisor of two another integers. So the first one is like first one is this condition. This is first. It must be a common divisor, right? And the second one is must be a positive number. And the third one is like this is third. This is the second. Is every common divisor of A and B is a divisor of D, which means D is multiple of all of A and B's common divisor. So let's see some examples. So one famous example of this one is the common divisors of 36 and 48. And they also, both of these numbers have a lot of divisors you can find here. So the common divisors of them, we just find the common divisor of 36 and 48, which is 1, 2, 3, 4, 6, 12. That's all. And the greatest common divisor is 12 because first of all, like it is by literally the greatest, and it satisfies first. It's already satisfied as a common divisor. Also, it satisfies is greater than 0. So we just need to prove every common divisor of them is a divisor. So 1 divides 12, 2 divides 12, 3, 4, they all divide 12, including the negative numbers. So it is the largest, the greatest common divisor. Okay. And a theorem regarding this one is, how to say, a theorem regarding the common divisor is if A, B are two integers and A is not equal to 0, B is not equal to 0, if they are not both 0, then A and B have a unique greatest common divisor. So one thing very interesting, why cannot we have both A and B equal to 0? Because in this case, a very interesting happened. Like for example, the common divisor of 0 and 0 is an infinite set. It is every integer because 0 have infinitely many divisors, and the common divisor of 2, 0 has infinitely many divisors. So it's an infinite set. As a result, it doesn't have a greatest common divisor. Okay, so why it only has a unique common divisor? So here we have to prove two things. First is the existence, and then it's the uniqueness. So the proof is very long. And first we want to make a abbreviation of greatest common divisor. We say, so here we say greatest common divisor. Let me see where I have written that. Yeah, greatest common divisor we always say is GCD, which is an abbreviation of the three words. We use 3 letters to abbreviate it. So it's GCD. Okay. So suppose D is the smallest positive integer in S, as is defined by here. So this proof is use the knowledge of the linear combination. It's from something called linear algebra. So maybe it's too advanced for the course for now. But if you have already studied some linear algebra content, then x a plus y b. This one is a linear combination of A and B because x, y is not fixed. A and B is fixed. It's fixed by here. is fixed by here, right? And if D is the smallest positive integer in S, and we want to find the smallest positive integer in S, here is actually the GCD, because by the while ordering principle, the natural number as is greater than 0, it will always have a smallest positive integer, right? Okay, and first we want to prove like if D is not divisible by A, then R is not 0, and we can write by the division algorithm, we can write in this form. And because R is equal to A minus DQ, and D is equal to this one by the set definition, there exists x1, x2 satisfied. And we can expand this form to write as this one. This is by A minus x AQ, and we abstract A out, and then we abstract B out from this form. And then we find, well, R is equal to something times A plus some integer times B. So which is a smaller positive number in S, right? Because R is a common divisor of like A and B right now. And because 1 minus x1 times B is smaller than 1 minus 2x q is smaller than the what we already find at the D. So R is smaller than D. So which is contradicted to 1 here. D is not the smallest integer here. So D must divide A. And by a similar approach, we can find D is also divided B. So D is a common divisor of A and B. And this is by the fact of these two statements. So yeah, so that's it. And we suppose D1 is any common divisor of A and B. And in this case, why we suppose D1 is any common divisor, we have to find like for all D1, D1 is also a divisor of D. So then we proved D is the GCD. Because this any is also a common divisor of A and B, then there exists A1 and B1. There exists A1 and B1 to satisfy A equal to D1 times A1, B equal to D1 times B1. So this equal to x1A plus x2B by the statement 1 definition here, right? And A is equal to this one, B is equal to this one, so we find this one. And this is equal to D times something. And this one is all formed by a linear combination of integer, which is also an integer. So D times D1 times integer, which means equal to D, which means like D1 is divisible, is a divisor of D. Okay, so in this case, we can find like D is the GCD of A and B by GCD's definition. Okay, and the uniqueness is proved by we first assume a D2, which is not equal to D, and we just to find out D2 is equal to D. This is by the definition of GCD, like D2 divides D and then D divides by D2, because like they are both greatest common divisors. So like when we considering D is a GCD, then D2 any divisor, because D2 is also a common divisor of A and B, so it must divide D, and D is also divisible by D2, and because like B is not equal to 0, so A must smaller equal to B. Like in this case, A is D2, B is D, right? And D is not equal to 0. So we found out like D2 must be smaller or equal to D, and by the later part, this part leads to this, and this part leads to this. D must be smaller or equal to D2, and we find they're both equal. And because like the GCD is always a positive number, so their absolute value is the same, means they are the same. So we show it's unique, such the GCD is unique. All right, and there another theorem is regarding the prime number again. So a easier case, a simpler case of this one is like if P is a prime number and if P divides AB, then P divides A and P divides B. Oh, not and, but or. So P divides A or P divides B. This theorem is like is helpful because if we know P is a prime number and this integer is something like 2, we can know it's 2 integer time together. A and B can be prime number, it cannot be prime number, but it's a multiplication of two integers. Then we can always find A or B that P can divide them. And this is the case when A, B, there's only two integers. And this is when they're infinite, not infinite, but like a very long list of like, how to say, integer multiplied together. And if P is a prime number, then P divides all them. If P divides them all time together, then there exists one AI in this one that P can divide AI. Okay. And I think this one is, you can think about it in this way, like P is a prime, so P can only be recognized as 1 times P, right? So if P like we can do a very direct proof of contradiction. If P divides A times B and P is not divisible by A nor B, then P must have two factors, one from A, one from B, and it's all smaller than P, which means P is not a prime number. So A or B must divide P. So that's a that's an intuitive proof of progress. And last thing we say today is we'll introduce is a concept called congruence. And congruence has some application in abstract algebra, also in divisibility test. Divisibility test is a test used to find like what type of number is usually divisible by 2, divisible by 3, divisible by 5, divisible by 10, and maybe some more advanced thing, what's the characteristic of a number divisible by 17. And this type of thing makes the central concentration about number theory. And another thing is about abstract algebra. Congruence forms something called a congruence class out of the set of integers, and we can expand it to some other mathematical system like rings, groups, semigroups, or albedo groups, and those will be seen in the abstract algebra courses. So we first define a congruence. So for AB, so for integer AB, and n is not only integer but a natural number. It's a positive integer, and A and B are said to be congruent modulo n if A minus B is divisible by n, or we could say like we can write in this form, and this indicates like n divides A minus B. So some intuitive thinking, we can see some examples below. 0 and 15 is 0, like 0 and 15 are modulus of congruence 5. They are modulus 5 because 0 minus 15 is negative 15 divided by 5 is negative 3, which is divisible. So in this case, 0 and 5, they are divisible. They are modulo 5. 5 negative 13, they are modulo 6 because 5 minus negative 13 is 18. 18 divides 6 equal to 3. It's also divisible. And in this case, even it's modulo by 1,000, but we minus them to find it's 5,000 and divides 1,000 equal to 5, which is also divisible. So these three example gives us one thing. It's like all of the numbers here is how to say so they give us a clue of how congruence class, not congruence class, but congruence relation means. And we can always write the congruence relation in some other ways. So in definition, and this character is usually very hard to think of when you first look at it. So you might need to look at several times and several days very frequently to recognize what it means. So you can have so next time you've seen it, absolutely mean you know the meaning of it. So A, we write this character here, B modulus M. We cannot always A just writing this. This doesn't mean anything. Or mod N, or mod, maybe we saw something called mod 5. This doesn't have any meaningful ideas. We must write them all together to have the meaning of like M is divisible by is a divisor of A minus B. Okay, some other ways to write this long character is there exists a K, integer K, such that A minus B is equal to MK, and this is by the definition of divisibility. Or we can say there exists an integer K, A is equal to B plus MK. Like you can say 16 is equal to 1 plus 3 times 5. So 1 and 16 is mod 3, right? Because 5 is integer, which means K here. All right, so there's one fact regarding the congruence is for all natural number n, the congruence modulo of n is an equivalence relation on the set of integers. So why is that? So how do you prove like equivalence relation? We need to prove three things: reflexive, symmetric, and transitive. And proof ideas is written here. I write some like basic ideas of it. It's not very serious, so you can look it later about how this one is. But congruence modulo n is always an equivalence relation for all n. And we'll talk about some applications of the congruence. The first one is divisibility test. Divisibility tests we have seen two. Like you already know, like 2 is all the number which can be divided by 2 always have one character. That is the any number is always 0, 4, 6, 8. And for 9, you probably know, like if an integer is multiple of 9, then the sum of its decimal digits is always a multiple of 9. And the decimal digit is defined here. It's like if A is a non-negative integer and is written in this form, like for example, A is equal to 951, and you can see it's made of 9, then 5, then 1, and each of them is a decimal digit. So each AI here is if it's between 0 and 9, for all of this A here, and we say AI is a decimal digit of integer A. And probably heard of like any number that is divisible by 9. The sum of its all this decimal digit is a multiple of 9 too. And but why this is true? we can use like if and only if proof to make sure it actually works. And the proving process uses the knowledge of congruence class. So for all n, so for all integer n, that is divisible 9. So suppose we suppose this part. Then n is equal to 9 times some k integer k plus 0. So this is divisibility's definition. And we can see here, because n is equal to 9 times k plus 0, then by the definition of congruence class, n and 0 are modulo 9. So because n can be written in the form, if we consider its decimal digit form, n is equal to ai times 10 to the power of pi. We sum it up because this is ideally like 591 is equal to 1 times 10 to the power of 0 plus 9 times 10 to the power of 1 times 5 times plus 5 times 10 to the power of 2 is equal to 1 plus 90 plus 500. So this is a way to write any positive integer in a decimal digit form. Then one interesting thing happened is that if n is equal to this form, then all of this plus together, we just expand this summation to here. And because of this one, right, we can say like this long number and n, they're modulo 9. And because and because 10 1 modulo 9, because 10 minus 1 is 9, which is divisible by 9. And we can always simplify all of the 10 into 1. And this is by the linear property or linear combination property of the modular of the congruence system, which we'll talk about in the abstract algebra. So this form, because 1 to the power anything is just 1, and we can ignore it. So this one is 0, is modulo 9. And this implies this whole sentence, this whole statement implies the sum of decimal digit. All of these are decimal digit right now. The sum of it is a multiple of 9. And this proves one direction. And if we want to prove another direction, we're just going back from 9. We just suppose all of the, like, if we're going back, we'll do something like that. First, we'll say the sum of the decimal digit is a multiple of 9. We first suppose it. And then it implies this one. And because like 10 modulo 1 modulo 9, we can replace 1 by 10. And we get this one. And n modulo 9. And n is divisible 9. So we're doing a vice versa process to complete the if and only if statement. Okay, and also for 11, maybe this is more less people heard about it. The characteristic of integers that is divisible by 11, but it is always stated like that. So an integer n equal to some decimal digits is divisible by 11 if and only if the number t minus 1. So minus 1 term, plus 1 term, minus 1 term, plus 1 term is divisible by 11. And this is proved very similarly. We just also write n in the decimal digit form. But because 10 and negative 1 are modulo by 11, so we just simplify 10 11 to like simplify the 10 here to negative 1 and negative 1. So it's negative 1 to the power of I is not always 1. It's 1 minus 1, 1 minus 1, 1 minus 1. And this leads to the form like that, which is equal to what we supposed to have. So what this actually means that these two here. And also we can do a converse operation. We just find this one. I'm going back to complete the if and only if relation. Okay, so that's a common application of the congruence. Actually, all of the 9, 11, they are just like specific form of a more general cases. The discussion of divisibility test. And another application of it is congruence is sometimes used to construct algebraic systems. Like the most common thing is called congruence class on integers. And from that, people know about rings, know about the conformal mappings. And aside of rings, we have polynomials, and we can form congruence classes on polynomials in the same logic as the congruence classes on integers. And there's also ideals, some more complex mathematical structures. So this is how the congruence is used. And the second point is an entire core system called abstract algebra. I'm not, I just study a little bit of abstract algebra. So if you want to learn about abstract algebra, you can look for information and some useful materials online. It's a very how to say, very old course, and already have like plenty of materials that you can learn from. So, but I just know a little bit about abstract algebra, so maybe I'm not helpful for showing all these things in that form.